Yeah. Okay. So hello everyone. So we were continuing this series of mass transfer short concepts. So we have already covered our last lecture. I think we covered our calculation of column diameter. Then equimolar counter diffusion has been covered. Adsorption topic has been covered, and dimensionless numbers involved in mass transfer has also been covered. So today let us look into mass transfer coefficients. Today let us look into mass transfer coefficients. Okay. So mass transfer coefficients. So what are mass transfer coefficients? What is mass transfer coefficients? So we said that for defining our flux, in case of diffusion, we can either define it from our conductive mass transfer or from our convective mass transfer. So what is the difference between our conductive mass transfer and convective mass transfer? So let us understand that first. So this is our diffusion. This diffusion will be of two types. One is our conductive and one is our convective. Okay. So what is the basic difference between these two? So suppose you have a sugar cube. A sugar cube is there, and there is a beaker full of water. Okay, this is a beaker full of water, and you place a sugar cube at the bottom of the beaker. This is our sugar cube, and rest everywhere water is present. It is a full of water beaker. Okay, so what are the steps that are going to happen? First, this sugar cube will dissolute. Dissolute means you will see that the sugar cube, once you place it, it will first dissolute. Dissolute means it will form a cloudy structure here. From like till this much area, a very cloudy structure will be formed. Okay, cloudy nature will be formed. Okay, now this cloudy nature, this thing is known as your dissolution. This phenomena is known as your dissolution. Once it dissolutes and it forms a cloudy nature, then what happens is that the concentration of the sugar at the bottom of the beaker becomes higher than the concentration of the sugar at the top level of the water. Like here, the sugar molecules will be present like a negligible amount of sugar molecules will be present here. Then as we go down, the amount of sugar molecule will be going on increasing, and at this region, this cloudy region, the sugar molecules will be present in very high concentration. So a concentration difference will be created between the sugar molecules from this region and this region, and due to this, what will happen is that our sugar molecules will start to transfer from this region to this region, that is from the region of high concentration to the region of low concentration. Our sugar molecules will travel, and this phenomena is nothing but our conductive diffusion, that is without any external force. We are not applying any external force, we have just put the sugar molecule in the beaker. So without any external force, our diffusion is happening just because of our concentration difference, and this is known as your conductive mass transfer. Clear? Okay. Now what will happen is that you take a spoon. Now what you do, you take a spoon, you put it inside the beaker and you stir it. You take a spoon, you put it inside the beaker and you stir it. Once you stir it, we are applying some external force, and the mass transfer will happen in that case also. In that case also, the sugar molecules will travel from this distance to this, from here to here, for everywhere it will get uniformly distributed among the entire beaker of water. So mass transfer is going to happen, but that kind of mass transfer that happens in the influence of some external force. Here in this case, the external force is our stirring. That kind of mass transfer is known as your convective mass transfer. Clear? So that is the basic difference of our conductive mass transfer and convective mass transfer. Okay. Now understand one more thing. That our conductive mass transfer, this was a very slow process. Slowly the sugar will dissolute, it will create a cloudy zone here. Then slowly, due to concentration difference, the sugar molecules will travel from high concentration to low concentration zone, and after a very long time we will get like uniformly distributed solution. Okay, so conductive mass transfer is a very slow process. Because this conductive mass transfer is a very slow process, so what is easy is that drawing the concentration profile or drawing the velocity profile of the sugar molecules is very easy. You getting it? No. As because this conductive mass transfer is a very slow process, so getting the concentration profile or the velocity profile is very easy. Okay, you consider two cases, no, that is diffusion of A through non-diffusing B, then equimolar counter diffusion. We have also seen non-equimolar counter diffusion. So in that diffusion of A through non-diffusing B and equimolar counter diffusion, you draw your concentration profiles. One is like this in the shape of a parabola, like exponential profile, and the other one is last linear profile. The equimolar counter diffusion has a linear profile, and this one is having a logarithmic or a exponential profile. So what happens is that, as because conductive mass transfer is very slow, so getting a the concentration profile and the velocity profile is very easy. However, as because this convective mass transfer, in case of the convective mass transfer, as because this convective mass transfer is very fast under the influence of some external force, so in that case, getting the concentration profile and the velocity profile of this convective mass transfer, it's a very complex. It becomes very complex and it is very difficult for us. You're getting it? So that's why what we do is that for this convective mass transfer, we write directly flux is equals to mass transfer coefficient and into driving force, and the mass transfer coefficient will be selected based on the selection of your driving force. In this case, in conductive mass transfer, we were directly deriving the equation of our flux. Yeah, your flux is Na. Your flux in mass transfer is denoted by Na. That is your either your kilomole per meter square per second. That is your, this is your flux. So flux it becomes what? It becomes a rate, that is kilomole per second per unit area. This is rate per unit area. That is, rate is your kilomole per second and area is your meter square. So from there you get the unit of flux as kilomole per meter square per second. Okay, so it is denoted by Na. So for conductive mass transfer, what we were doing is that we were deriving the equation of our flux. But in what we say that in case of convective mass transfer, as because there is some external force, in that case what is going to happen is that the derivation of the directly the equation of the flux is not possible, as because the concentration profile or the velocity profile becomes very complex. So what we do is that for convective mass transfer, we write our Na, that is our flux, directly equals to mass transfer coefficient and into driving force, and into driving force, and this mass transfer coefficient is selected based on what driving force we are going to use. Okay, mass transfer coefficient is selected based on what driving force we are going to use. Okay, now let us move forward. Let us move forward. So we say that our Na will be is equals to mtc, that is your mass transfer coefficient, into our driving force F. Okay, very good. So what are the kinds of driving force? The first one is concentration difference. So concentration difference, if we are getting, so we denote it by delta Ca. Which is equals to Ca1 minus Ca2. If your driving force is concentration difference, then your mass transfer coefficient is denoted by, let it be Kc. Your mass transfer coefficient is denoted by Kc. Let it be small kc. Better, okay. Let us denote by small kc. Now what will be the unit of this small kc? So this unit of the mass transfer coefficient, depends on the driving force. How? You know that your flux is equals to mass transfer coefficient into your driving force. The unit of flux is fixed, that is your kilomole per meter square second, and that is equal to mass transfer coefficient, let it be mtc, and your driving force. In this case your driving force is concentration difference. So what is the unit of concentration? It is kilomole per meter cube. So what is the unit of your mass transfer coefficient? It comes kilomole will get cancelled, meter square and meter will get cancelled, and you will get your mass transfer coefficient unit as meter per second. So what is the unit of kc? It is meter per second. And what was the unit of your concentration? It was mole, let it be kilomole per meter cube. Clear? So from here we can say that your mass transfer coefficient is equals to flux divided by your driving force, This will be your mass transfer coefficient. Clear? And in case your driving force is your concentration difference, that is delta Ca, that is Ca1 minus Ca2, in that case the unit of the mass transfer coefficient will be meter per second, and we denote it by Kc. We denote it by Kc. Okay. Let us now go to partial pressure difference. What if your driving force is partial pressure difference? What if your driving force is partial pressure difference? That is delta Pa. If your driving force is delta Pa, that is partial pressure difference, that is Pa bar 1 minus Pa bar 2, in that case your mass transfer coefficient will be is equals to, we denote it by Kg. We denote it by Kg, and in that case our flux, that is our Na, is equals to Kg and into Pa bar minus Pa2, like this. Okay. In this case, in the previous case, for concentration difference, our flux Na was defined as Kc into Ca1 minus Ca2, like this. Okay. And what will be the unit of our Kc? Then that will be our just the flux divided by the driving force. In this case also, if you want to find out the unit of your Kg, so just do the flux divided by your driving force. So in case of flux, what is the unit of flux? It is kilomole per meter square second, and your driving force is your pressure, so it is Pascal. So this will be your unit of your Kg. Now if you want to more simplify it more, then you may do it. You may simplify it, but it is not required. You just understand that how to find out the unit of your mass transfer coefficient based on your driving force. Okay, that is important part. Okay, so in this case the driving force was our partial pressure difference. Let us now move forward. And let it be mole fraction. Now this mole fraction again can be of two types. One is your gaseous phase, and one is your liquid phase. If it is gaseous phase, then our flux Na is equals to, we denote mass transfer coefficient, we denote it by Ky, and it is Ya1 minus Ya2, and in this case our Na is equals to small kx. In that case it becomes Xa1 minus Xa2, and it is very clear that because mole fraction is having no unit, so the unit of the mass transfer coefficient Ky and Kx will be same as the unit of the flux. Very easy. As because your mole fractions are dimensionless, mole fraction is not going to have any unit, so in that case what is going to happen is that the unit of your mass transfer coefficient will be just equals to the unit of your flux. So what are the units of your Ky and Kx? It is just equals to it is just equals to your unit of your flux, that is your kilomole per meter square second. Okay, normally. So this is for mass transfer. Suppose you want to do heat transfer. So in heat transfer what we do? Again the same thing, that is your flux is equals to heat transfer coefficient and into driving force. Now for heat transfer your driving force is constant, that is your temperature difference. It cannot be anything else. For mass transfer it can be concentration difference, partial pressure difference, mole fraction difference in case of for gaseous phase, mole fraction difference for liquid phase. But for heat transfer, your temperature difference is only your driving force. So then in that case your heat transfer coefficient is equals to flux and divided by delta T. What is the unit of heat flux? Again the same thing, it is just rate per unit area, and this delta T will have unit Kelvin. So this will become the unit of your heat transfer coefficient, and you all know that heat transfer coefficient we denote it by small h, and what is the unit of small h? Watt per meter square Kelvin or watt per meter square degree centigrade. This is only we use. Okay, how is it rate? Suppose this Q is your flux, no? Q is your flux. So what is the rate? What is the unit of heat? The unit of heat is kilojoule or joule. This is the unit of heat. Once we convert it to rate, we divide it by second. Here also we convert divide it by second. If it is joule per second, it becomes watt. If it is kilojoule per second, then it becomes kilowatt. So watt represents the rate. So flux will become watt per meter square, and this flux is nothing but your small q. So here see the flux, in place of flux we have written watt per meter square, and this delta T will have a unit of Kelvin or degree centigrade. From there we will get this Kelvin or degree centigrade. Clear? So this was the basic idea of our mass transfer coefficient, and in comparison also heat transfer coefficient for our this subject. Okay, so now let us end this lecture here, and in the next part of this lecture, like in the following lecture in the series, following lecture of this series, we will discuss that what are the values of the mass transfer coefficients for specific cases, that is your diffusion of A through non-diffusing B, and for equimolar counter diffusion, that we will see. And we will also see that what is the relation between your Kc, Kg or different mass transfer coefficients. So how to find the relation between the different mass transfer coefficients, that also we will see in the next lecture. Okay, thank you. If you have any concern, you may contact the number that is at the bottom of the screen, or we will meet in the next lecture with the second part of this lecture concept. Okay.